Imagine trying to scoop up a single tablespoon of matter, only to find that this tiny amount weighs a billion tons. On Earth, it is physically impossible to hold, let alone contain. To understand how something this heavy could even exist, we have to look backward to the violent death of a massive star, one that started its life roughly 8 to 20 times the size of our own sun. This visualization shows the delicate balance that keeps a star alive. For millions of years, the outward pressure of nuclear fusion pushes against the crushing inward force of gravity. But when the fuel runs out, fusion stops, and gravity takes over entirely. The outer layers of the star collapse inward, hit the dense core, and rebound in a colossal supernova. It is one of the largest explosions in the universe, completely obliterating the star's exterior while violently crushing the core deeper into itself. When gravity prevails over the core's resistance, the leftover matter is forged under extreme conditions that break the normal laws of physics. When the dust from the supernova clears, the object left behind in the void is a neutron star. This remnant still retains a mass greater than our entire sun, but the collapse has compressed all of that material into a sphere measuring just 12 miles or 20 kilometers across. To see exactly what that compression means, look at this scale comparison. If you took that entire solar mass and brought it to Earth, it would barely cover the footprint of Manhattan Island. Forcing an entire sun into the physical dimensions of a single city crushes the most basic building blocks of matter together. The resulting density creates an object that entirely defies human interaction. Inside that 12-mile sphere, the immense gravity squeezes the atoms so tightly that protons and electrons are forced to fuse together, leaving behind a dense, solid core of pure neutrons. This diagram illustrates the only physical force capable of stopping those neutrons from collapsing further into a black hole: neutron degeneracy pressure. The neutrons violently repel each other, pushing back against the crushing weight of the star. Now, return to the idea of taking a single spoonful of this ultra-dense matter and magically transporting it to the surface of the Earth. The moment it arrives, the immense gravity is gone. Without that gravity holding the matter together, the neutron degeneracy pressure is instantly unleashed. The tightly packed neutrons expand outward at a terrifying speed. The resulting kinetic shockwave acts like a cataclysmic bomb, vaporizing a massive chunk of our planet in a fraction of a second. The matter inside a neutron star only exists because it is trapped by its own crushing gravity. Removing it from that delicate balance turns it into a lethal explosive. The same collapse that creates this density also forces the remnant to spin at terrifying speeds. As the star's radius shrinks, its rotation accelerates through the conservation of angular momentum. In this image of a pulsar wind nebula, the bright center holds a rapidly spinning neutron star. We call these specific stars pulsars because they emit sweeping beams of high-energy radiation from their magnetic poles, flashing across space like cosmic lighthouses. The fastest known pulsar, PSR J1748-2446 AD, completes 43,000 rotations every single minute. That is twice as fast as the blades in a household blender. Because this rotation is so incredibly consistent, pulsars track time more accurately than our best atomic clocks. Physicists rely on these spinning remnants as precise timing mechanisms to measure distances and celestial movements across the cosmos. On the right side of this illustration, you can see the intense magnetic loops of a rare variant called a magnetar. Its magnetic field is 1,000 times stronger than a typical pulsar and trillions of times stronger than Earth's. This intense magnetic strain physically locks with the solid crust of the neutron star. Over time, the magnetic field twists and pulls, building up incomprehensible physical tension. Eventually, the crust reaches its breaking point. The tension snaps, violently rupturing the surface of the star in an event known as a starquake. When a starquake occurred on the magnetar SGR 180620, a single rupture lasting just 1/10 of a second released more energy than our sun emits in 100,000 years. The sheer output of these ruptures proves that even the solid, dead surface of a neutron star remains a volatile battleground of physical forces. Since these stars often form in binary pairs, Astronomers naturally asked what happens when two of these impossibly dense objects eventually spiral inward and collide. The impact of a neutron-star merger is so violent that it physically tears the fabric of spacetime, creating gravitational waves that ripple outward across the universe at the speed of light. This is a concrete arm of the LIGO detector on Earth. In 2017, instruments exactly like this one successfully captured the microscopic spacetime ripples from a distant neutron-star collision known as GW170817. By successfully detecting these invisible waves, astronomers verified that extreme mass colliding in the deep universe can literally stretch and squeeze the physical space we occupy here on Earth. But there is a sharp contrast between what we can measure and what we can see. We can feel the ripples of their collisions across millions of light years, yet we are completely blind to what exists inside the actual stars. Physicists call this the equation of state. It is a decades-old, unsolved problem regarding exactly how matter behaves at the absolute center of a neutron star. The internal pressure is so high that current models of physics fail to describe how matter behaves at the absolute center, leaving the specific composition of the deep core unknown. If a star the size of a city can outweigh the sun, what else in the universe is hiding behind a scale our brains were never built to understand? These objects exist at the absolute limits of reality, daring us to rewrite the laws of physics just to comprehend what they are.